They have the layer of stuff down.
Down here, I felt like it was nothing. So long from south.
Okay, everyone shut up now.
All right.
Okay, so the first thing, the most important thing is the exam on Thursday. So remember that. Exam 2 is Thursday. That would be 11/2. And the topics are everything up through Newton's laws. And remember, that includes stuff that was on the last exam. So you need to refresh your memory about the old stuff. And I'm just planning to do some example problems today with Newton's law type stuff, give you time to work on it, and then I'll go through it just to make sure that that stuff is clear to you. And then I also want to say, so this is the pressing thing, but also lab exam 2 is next week in lab. And the topics for that are everything from the labs through the review that we did last week. So the stuff that we're doing this week is not on it. So I think that means that it's all the topics from the labs up through like 2D acceleration and net force direction. Okay. And remember, this is cumulative too. Everything I do in this class is cumulative, so you got to go back and refresh your memory. Anybody have any questions about either of these? Or any homework questions related to the exam on Thursday? Okay. Well, let's just go into some problems, some different types of Newton's laws problems, and you can think of it as a little study time while I'm here and other people are here to, get you on the right track if you're misunderstanding something. Exam pull is what I mean. Okay, so let's start with a horizontal surface. And two objects connected by a cable. And 100 Newton force pulling to the right, and 150 Newton force pulling to the left. And you want to calculate two things. The acceleration vector. It doesn't matter which one you do the acceleration for, it's all the same. And second, the force on the 10 kilogram by that cable in the middle. So let's break it up into pieces. If you finish the first piece, feel free to go ahead and work on the second piece. But let's start by calculating the acceleration of the system, and then I'll go through it and you can sort of check your steps. And then we'll go on to B. I'll give you time to go on to B. So go ahead and work on that. Calculate the acceleration. This is almost always on these problems the best way to start. What are you going to isolate? What are you going to draw a free body diagram of to calculate the acceleration? You can do each mass. That's 2 steps, though. You can do it in 1 step by isolating the whole thing. So that's what I'm going to do. So what we've done is when the accelerations of the two things are different, like when there's a pulley involved, that's when you have to isolate the individual bodies first. There's no way around that. But if they have the same acceleration, you pretty much always are best off isolating everything together. Okay, so there's a weight force down. The total mass is 15 kilograms, so this is a weight of 147.15. There's a pushing force up, I'll call that N total. There's a 100 to the right and a 150 to the left. And that's everything, because if you continue around the boundary of this outline, there aren't any other places the surroundings make contact. So now I'll go to Newton's second law. Negative 150, 0, plus 0, negative 147.15, plus 0 N total, plus 100, 0, is equal to the mass, 15, times the acceleration, a0, there are two equations here, but we're trying to calculate the acceleration vector, which is this. And so you can see that we'll know the acceleration vector as soon as we figure out a. So I'm just going to use the x equation. So negative 150 plus 0 plus 100 is equal to 15a. And so negative 50 is equal to 15a. And so that says a is equal to negative 3.3 repeating meters per second squared. Well, I didn't ask for the variable a, I asked for the acceleration vector. So now we want to plug this back into that vector. And what we get is negative 3.3 repeating 0. Or if you want to visualize it, that's in the negative x direction with a magnitude of 3.3 repeating.
Would you accept either the arrow or the...
Yes, either one is fine. Yep, that's true of any vector. You can always give your vector answers. Obviously, you can always give them as components, but you can also always give them as just an arrow and a magnitude. Okay, well, this is the acceleration of the whole thing. It's also the acceleration of the 10 kilogram and also the acceleration of the 5. So now you can use this isolating either body. So now take a couple minutes and see if you can take the next step of calculating the force vector on the 10 by the cable. All right, so, well, by default, we're looking for a force that's on the 10, so I guess I'll isolate the 10. You really don't have to. You could isolate the 5 and then use what you know about cable forces to figure out the answer. But free body diagram on the 10 kilogram. We have a downward force of 10 times 9.81, so 98.1. We have a pushing force from the ground. That's not the same one that we had in this one. This was the combined pushing force on both of those two. So I'm going to call this one N10. And then we have the 150 Newton force this way. And then the last thing I'm putting in is the pulling force from the cable this way. So Newton's second law says negative 150, 0, plus 0, negative 98.1, plus 0 and 10, plus t0 is equal to the mass, 10, times the acceleration, which now we know. If we didn't know this, we'd have too many variables and we wouldn't be able to solve for the force. Well, we're looking for this. This here is the force vector on the 10 by the cable. In order to express that force vector, we need to figure out the variable t. So I'm going to use the x equation. It says negative 150 plus t is equal to negative 33.3 repeating. And so t is equal to positive 116.6 newtons. And so the force vector on the 10 by the cable, you can plug this into that force vector and you get positive 116.6 repeating 0. Or another way to think about it is this is what we're looking for, the force vector on the 10 by the cable. And so it has a magnitude of 116.6 repeating in the direction of that arrow. Any questions about that? Okay. Let's go on to a different type. Oh, want to see something interesting? If you applied, I mean, that's sort of relative. But if you applied this set of forces over some amount of time, what could you figure out about the motion of this thing? So let's say what if those forces were applied for 5 seconds to a system initially at rest? How fast would the objects be moving? Okay, well, we have a system like this. Let's choose a 0 position. This is a one-dimensional motion, right? So let's choose a 0 position to be where the left end of the left object is at time equals 0. And we'll say the positive direction is, well, this is in 2D, so instead of doing it like this, let's do it like a 2D problem. I mean, it's a one-dimensional motion, but I have everything in terms of vectors, so let's just use the vectors for this. You could do it as a 1D problem too, but I'm going to just use the vectors we have. So let's say our coordinate system is, our origin is there. And our time equals 0 is going to be at the start of the motion, and our time final is going to be 5 seconds. And now let's think about what we know and what we want. We know TF is 5 seconds. We know the acceleration is negative 3.3 repeating 0. We know the initial position is 0. We don't know the final position. We know the initial velocity is zeros. And we're trying to find the final velocity vector. That means finding two components, so we're going to have to do two calculations for that. But the equations that'll work, we can use Vfx is equal to Vix plus Ax Tf. And we can use Vfy is equal to Viy plus Ay Tf. The x equation says Vfx is equal to 0 plus negative 3.3 repeating times 5. So Vfx is, oh, well, that should be negative 16.6 repeating. Vfy is equal to 0 plus the y component of the acceleration is 0. So Vfy is 0. And so the final velocity after those 5 seconds is negative 16.6 repeating 0. Or in other words, that's in the negative x direction. So it's moving this way at 16.6 meters per second. So if you know, when you calculate those accelerations in problems like this, if you know those accelerations are going to be constant over some amount of time, you can always use this stuff with the constant acceleration equations. What about circular motion? Could you use this stuff with circular motion? So, yeah, that's right. You cannot use this with circular motion, even if you have uniform circular motion and you know that your acceleration is only going to be centripetal acceleration. You can't use it because the direction of that centripetal acceleration is going to be changing as time goes by. And if the direction of an acceleration is changing, that's not constant acceleration. Constant means the vector components stay the same the whole time. Okay, so that's enough of that, I guess. So let's go back to the stuff that could potentially be on the test. Yeah?
Meters per second squared, but it's only acceleration, not a vector?
It's, this is a velocity.
Or velocity, okay.
Yeah, so any velocity, whether it's a vector or just a 1D thing, is meters per second. Yep, that's right. If you've taken, forget that. Okay. So the next one, let's say that we have a ramp that makes an angle of 20 degrees with the horizontal. And you have a 2 kilogram mass that's initially moving up the ramp. And let's say that the coefficient of friction is 0.2. What's the acceleration vector of the block? And is it speeding up or slowing down? Okay, take a few minutes and see if you can work through that. Just do all of it together this time, that second part. So for this, we're going to use a rotated coordinate system because it's on an incline. The y-axis goes out of the incline. That means, in this case, the x-axis goes down the incline. A free body diagram looks like this. So there's the body. The weight force is straight down, and that's 2 times 9.81, so 19.62. Then there's a pushing force that's perpendicular to the surface toward the body. And then last, there's a friction force, and that friction force is always opposite the direction that the thing is moving. So in this case, that friction force is this way. And the magnitude of this is the coefficient times that force pushing these two together. That N is in the positive Y direction, and the friction force is in the positive X direction, but we have to figure out the components of the weight force. That's always the kind of the most complicated step of these kind of problems. So to do that, let me draw the coordinate system. The weight force is straight down. The angle between the 270 line, that's this, and the weight force is always the angle between the horizontal and the incline, so this is 20 degrees. Okay, so now what's the angle that you have to go counterclockwise from the x-axis to get to the weight force? Yeah, 290. So we're going to go 19.62 times the cosine of 290, 19.62 times the sine of 290. Oh, it's the one without a battery. Okay, 19.62 times cosine of 290 and sine of 290. So you get 6.71 for the x component, negative 18.44 for the y component. Now Newton's second law says, so I'll put the weight in first, 6.71 negative 18.44. So that is this 19.62 here. And then we got 0n plus 0.2n0 is equal to the mass, 2 kilograms, times the acceleration. Is this going to accelerate along x or along y? X, so this is a0. All right, so now you got two equations. I'll write them out. So 6.71 plus 0.2n is equal to 2a. And negative 18.44 plus n is equal to 0. So how are we going to solve this system? Yep.
Don't you have to solve for n and then
Yep.
top?
Yep. Always on these, that's the set of steps you take. So use the y equation to find n, then plug that into x. So this one tells us n is equal to 18.44. Then put that into the x equation, you get 6.71 plus 0.2 times 18.44 is equal to 2a. And so a is equal to 5.20 meters per second squared. So the acceleration vector then, plug that into your acceleration vector and you get 5.200. Or in other words, it's down the ramp at 5.20 meters per second squared. So in this case, is it speeding up or slowing down?
Slow down.
Very good. Yeah, so the velocity and acceleration are in, what did I say, opposite directions. And so it's slowing down. So you could, if you wanted to calculate, if you knew what its starting velocity was and you wanted to calculate how long it was going to take to stop, how could you go about that? Yeah, you could use the constant acceleration equations here and figure out how far it would go before it stopped or how long it would take before it stopped or things like that. Okay. Any questions about the process on that one? Okay. Let's do one that's sort of the third type of this kind of problem. So let's say we have a ramp that makes a 30-degree angle with the horizontal. And we have a cart with a mass of 1 kilogram. And it's connected by a pulley to a mass that's hanging. Let's say this mass is 0.5 kilograms. What's the acceleration vector of the hanging mass? Just so that we can all, we can kind of carefully compare steps. Let's what we're going to do is we're going to isolate each of these individually. We have to in this case because the accelerations of the two things are going to be different. Okay, so let's start by isolating the 1 kilogram. So we'll start there. Then second, isolate the hanging mass and then go through it that way. Right now, just come up with a free body diagram for the 1 kilogram cart and the equation that you're going to use in the system of equations from this, okay? Then I'll do that and then we'll go on to the next one. Okay, so, well, one thing about this is we're going to use a rotated coordinate system on this one and a regular coordinate system on this one. The free body diagram of the cart. By the way, I think I might have just randomly chosen numbers that are going to give 0 acceleration. Okay, well, we'll fix that in a second. Okay, so there's a weight force that's 1 times 9.81. A normal force, and then a pulling force from the cable. To represent the weight force in this rotated coordinate system, this is the 270 degree line. This angle is 30 degrees. And so the angle from the positive x counterclockwise to the vector is 270 minus 30. So we're going to have 9.81 times the cosine of 240, 9.81 times the sine of 240. And you get negative 4.905, negative 8.5. And so Newton's second law says negative 4.905, negative 8.50 plus 0n plus t0 is equal to the mass of 1 times the acceleration. This is our first body. So on this one, you don't have to think about the direction at all. You can just do it the way that you would if it was by itself. We just think, okay, it's along the x-axis, so I'm going to write this as a0. And we don't have to think about up or down the ramp. The acceleration and the cable tension are in the x direction. So I'm going to use the x equation. It says negative 4.905 plus t is equal to a. And that's the one that's going to be useful later. We can't solve it yet because it's two variables in one equation, but we'll come back to it. Okay, now take a couple minutes and isolate the 0.5 kilogram mass. And remember, this is the one where you have to be careful with the directions, the second one.